When you think about where water comes from, where it goes, we can think about it in terms of a budget. So we're going to write out some water budgets here. Um, on the on a global scale, you all know where most of the water is. It's in the oceans. The oceans account for 97.2% of all the water. Where would the next big blob of water be? Think about it for a second. Where's the water? It's in glaciers, most notably Antarctica, but also Greenland, 2.1%. After that, maybe somewhat surprisingly, it's not the Great Lakes, it's not the rivers and streams, it's groundwater, 0.6%. Surface water, which includes the ponds and lakes and rivers, is 0.01%. And then there's a trivial amount that's in the soil. When we think about the volume of water, we have 1.3 times 10 to the ninth, so 1.3 billion cubic kilometers in the oceans, 2.9 times 10 to the seventh, so what is that, 29 million cubic kilometers in the glaciers, and groundwater, 8.4 times 10 to the sixth, 8.4 million cubic kilometers of water. Just in contrast to all that, the amount of water that's in lakes and streams is 2 times 10 to the fifth. So what is that? 20,000? 200,000? 2 times 10 to the fifth would be, let's see, 2, 1, 2, 3, 4, 5, 200,000. 200,000 cubic kilometers. That's in rivers and streams. The amount that's in organisms, mostly trees, 6 times 10 to the 2. You can see how much smaller that is. That's organisms, and so forth. Okay, and we talked a little bit the other day about the hydrologic cycle and how water moves between each one of these reservoirs. So we can think about hydrologic budgets on a global scale. So for example, we're continually warming the atmosphere and warming the oceans. So the oceans are going to be gaining water relative to the glaciers, and so forth. But we can also think about water budgets for individual basins or even reservoirs. And the budget that you'd use for a basin, obviously, is, or anything, if you think of it like how much water is in your bathtub, it's how much goes in versus how much goes out. So if you have the plug closed in your bathtub and you're adding water to it, the water levels are going to rise. If you turn off the water and you open the plug, the water levels are going to drop. But if you have water coming in and water going out, in other words, you have water coming into the tub and you have the drain open, you're going to have some balance there. If it's coming in faster than it's going out, the water levels will rise. If it's going out faster than it's coming in, the water levels will fall, and so forth. So let's think a little bit about how water gets into a basin. How does water get into a watershed, for example? How does water get in? It's pretty straightforward. There's only one way in, and that's through precipitation. The water has to be evaporated from somewhere, carried through the atmosphere, condense, and fall as rain, sleet, snow, or hail. How does the water get out, however? That's a little bit more interesting. So there are lots of ways that water can get out of a watershed. I'll give you a second to think about that and see if you can come up with 3 or 4. I'm just going to sit here and think while you come up with 4 ways that water can leave a watershed. Okay, so you probably got a lot of these already, right? So first of all, and most easily, is it runs off. It runs off in the form of water running over the land surface, or probably more importantly, through streams. It can also evaporate directly out of the system back to the atmosphere. It can transpire. Transpiration is a really important part of, particularly during the growing season, it's a particularly very important mechanism by which water is taken out of the ground and put back to the atmosphere. And evaporation and transpiration are very hard to distinguish between in a lot of cases, in terms of when you're just measuring how water is lost. And so they're often coupled into what's called ET, which just stands for evapotranspiration. So you all know what evaporation is, right? Just the water going from the liquid phase to the gas phase. But transpiration involves water being taken in by the roots of a plant and then released through the stomata during photosynthesis. So they are bringing carbon dioxide in to eat through their stomata and their leaves, and as a result, water can escape. And this can be on the order of, this can be enormous. These phreatophytic plants, like certain trees that live along riverbanks, like cottonwoods, are sucking up water like crazy and basically pumping it right back into the atmosphere. And then the final way, back to this list, the final way that we can remove water from the basin, from the catchment basin, is through groundwater recharge. We haven't talked about either of those terms really, but groundwater is the water that exists below ground in the pore spaces, and the water will soak into the ground, become part of the groundwater, and from there it can move outside of our water basin. When we think about reservoirs, right? Reservoirs are particularly important out west, where you have a river flowing down, and then you put a dam there, and you get a big reservoir behind the dam, right? And then you let water out from below the dam. Again, there's a dam. And these reservoirs, boy, that's terrible, but hopefully you get the gist here. That's a river. These reservoirs are used for a lot of purposes, right? They're used for hydroelectric power, hydroelectric, so the water that rushes out at the bottom of the dam turns turbines inside, and that makes electricity. They're used for recreation, so if you've ever seen all the houseboats on Lake Mead and so forth. But the biggest reasons that these reservoirs are there is to provide a stable source of water for drinking and agriculture. And when we start reading, I guess by this point in the class, you've already started to read, or maybe you started to read Cadillac Desert. But when you get to Cadillac Desert, you realize what an incredibly powerful thing these dams and reservoirs are, monetarily, politically, socially, and so forth. They are what make the West, and without these dams, the West would disappear overnight. Okay, so how do we think about water in agriculture and drinking? Well, there's a kind of an arcane way that we think about water, and it goes back to the old irrigation days. So in the old days, you have these ditches, which are quite small, and they run uphill of your field. So your field is down here, and here's your field, and you're growing it's supposed to be corn or whatever it is you're growing, right, down in the field. And the water is flowing like this. It comes out of a river, and it's flowing through a little ditch, and you just block it up, put a piece of metal down there, you block it, and then you open a little valve here, and the water comes spilling out of the ditch and floods across your field, and you let that water drain across and soak in, and that waters your crops. And when you're done, you close this valve and lift this up, and the water continues down the ditch again to the next farmer. So farmers' fields are generally in acres, right? An acre is scoop this up. An acre is a unit of area that's used. An acre is used for farmers' fields. And so the unit of volume that's often used for water is an acre foot. An acre foot is the amount of water that's required to cover 1 acre of land 1 foot deep in water. So this field is 1 acre. If you cover it 1 foot deep in water, that's 1 acre foot. So it's just a unit of volume. So if you have a reservoir like this one here, that is, who knows, 10,000 acres, that's the surface area of the reservoir, and the water level drops by 1 foot, because you're in a drought, unless water's coming in and is going out, then you've lost 10,000 acre feet of water, right? That's the volume. So you need to know that, because I'm going to have you do a calculation about calculating the hydrologic budget for a reservoir. Anyway, it's an arcane way of keeping track of water, but it's still used.